to gait cycle, which is really articulating, striding. Understand cadence, step frequency. And then I'll pretty much leave it there. It's not a huge amount of information. And again, it's just an introduction. We'll look at it more later in your career. You'll definitely play with it more within PT school. So as long as you have the basics and can articulate what people should be doing, you can start doing assessments of going, man, that's weird. So let's figure out why it's weird. Okay? Okay. All right, cool. So, spine. 33 vertebrae. We've got it broken down into 4 principal regions: cervical, thoracic, lumbar, and then we get into your sacral area, sacral and coccyx blending together. Now each of those is a unique bone until you get down into the sacrum. The sacrum is actually 5 vertebrae fused together, making one massive lump. And the coccyx is 4. Happy little tailbone sticking on the bottom. Closest remnant we have to a tail.
Why do some places say 5?
5 what?
For
They're lying to you. No, you'll see some adjustments with the sacrum. You can actually have a lumbarization or sacralization in which the 5th lumbar vertebra is actually fused with the sacrum, making it 6. Or you can have others to where the 1st sacral vertebra is disconnected, making it a 6th lumbar vertebra. But most people, 7 cervical, 12 thoracic, 5 lumbar, 5 sacral, 4 coccyx. So, again, people's Legos get put together in a little bit different ways, which may or may not be good or bad. So, 2 major parts in looking at any given vertebra piece. We have the body itself, which is stacked on top of each other. And then we have all kinds of funky projections from that offer attachment points, landmarks, and protection around. So the core is the body, which is passing the central weight from top to bottom. And you imagine your head weighs less than your head plus your shoulders plus your thoracic cavity. So the cervical vertebra, the cervical vertebral bodies are going to be considerably less bulky size-wise than the lumbar. Lumbar, you get big, stock, heavy-duty chunks of bone. Cervical, sometimes you don't even have cervical bodies. So, and then based upon the needs of that region of the spine, cervical, thoracic, and lumbar, it's going to change the appearance and the look, because that appearance and look is reflecting a purpose. When I give you pictures, when I give you examples of a vertebra, I'll typically pick a more mid-range piece so it reflects the unique qualities of that region a bit more vividly. So if I'm going to give you a thoracic vertebra to identify or play with, it's going to be more T7, T6, somewhere in the middle of that 12. So it doesn't look a whole lot like the cervical or a whole lot like the lumbar. So you've got a pretty good basis for understanding kind of what, well, it's easier to differentiate at this point. All right, so major points. The body we talked about, the centrum. And then off of that, you have 2 pedicles, which is 2 points, 2 bridges that come off to the side that connect you into these transverse processes. And then there's a lamina here and here that connect the transverse process into the spinous process. So, pedicles, lamina, transverse process, spinous process. So reach behind your neck. reach down, and you'll find that one of your spinous processes is the most prominent, that kind of pokes out right at the base of your neck. That's C7. And so you can actually work your way up about a finger width, and then you'll find the next one, and then the next one, so you can count your way up to about C4, sometimes catching C3. C2 and 1 are not palpable from that manner. Large part because their morphology, their structure looks a little different as well. So what goes in here? What's in the big hole? Your spinal cord. And it gives us the spacing to have it protected. You'll hear the term stenosis. You ever learned that term in medical terminology? Do you remember that term? Narrowing. So you can have spinal cord stenosis to where that vertebral foramen is actually closing in on the spinal cord, which means that shifting that you normally do is going to put pressure on it easier, so you'll get some radiating issues, radiculopathy. Now what's not very visible in this picture is this, the superior articular process, or facet. There's a superior, which means there's probably an inferior. So on either side, above and below, bilateral of the spinous process, you have two superior articular facets. And on the bottom, underneath that, you have the same thing, inferior articular facets, processes. Those are articulation points with this vertebra above and below. So the inferior articular facet of L3 is going to articulate with the superior articular facet of L4. They help provide shear force resistance to where it's not shifting back and forth. It can't come off. The vertebral bodies that stacked on top of each other, it gives a prevention from them slipping anterior and posterior off of each other. So how do we stack these together? The outsides of the bones are largely made up of cortical bone, compact bone, to handle that compressive force, that downward force of stacking bricks on top of each other. So the principal force that our spine is going through is a compression based. To every step you take, your mass is coming down with the line of gravity to help you move forward. This reinforces to make sure we don't have issues. The internal has a strutwork of trabecular bone, a spongy bone. So they can handle a little bit of shear forces, anterior, posterior, lateral, a little rotation. Take somebody who falls off a ladder and they land in a seated position. And you're going to get a significant compressive force that actually collapses the vertebral body structures because it's overloaded that cortical bone. And you got some major issues with that individual. So stresses are always greater on cortical bone than on trabecular bone, on the anterior side than the posterior side. So put that in perspective for a second. If we look at our skeleton over here. So our spinal cord very much sits in the posterior quadrant of our bodies, of that chamber. All of these projections, all of the vertebral foramen, the transverse processes, the spinous process, I mean, in many ways, some of these pieces are actually palpable posteriorly, superficially. So the vertebral bodies are sitting anterior. And the majority of our weight is sitting anterior, where we are leaning forward. Somewhat balanced and supported in the posterior in the back. So because of that, our load is very much pushing, kind of stacking on these vertebral bodies more anteriorly than posteriorly. Okay? Cortical covering thickened on a rim of superior and inferior plateaus centered by a layer of hyaline cartilage with a cartilaginous end plate. So above and below these vertebral bodies, we're putting articular cartilage. So it's reinforced to help make sure that we're not getting bone-on-bone rubbing. But then we have this cartilaginous end plate as well, which again just helps try to increase some of the rigidity. trabecular bone makes up an inner strut system. Two primary directions: vertical orientation to resist compressive forces to support that cortical bone, the longitudinal orientation to resist shear forces. Just like everywhere else, this trabecular bone is a strut work of internal spider webs that help give some internal rigidity so that we can handle more forces than just compression. Now, going from a vertical orientation versus a longitudinal orientation, the overlap of those, it actually creates a bit of a weakness in the anterior vertebral body. Because they don't directly intersect, there's a gap between them so that strut work isn't perfect, and it leaves a little bit of a weakness in the anterior body, which leads for an increased chance of collapse if we have too big of a compression force on our body, landing hard. All right, so quite a bit of what we just saw. This picture, though, helps articulate a little bit better this superior and inferior articular facets. So pedicle is here, so vertebral body, pedicle. And then we go into our transverse process, the other side of which would be the lamina going into the spinous process. So on that pedicle going out into that transverse process, we have a superior projection. This is a lumbar vertebra. The orientation of this facet joint of this superior articular process and this inferior articular process is nearly vertical at this point in the body. And this is one of those pieces that's going to change based upon where you are by region. So in the lumbar spine, this is a vertical orientation. Not yet, we'll come back to it. Oh goodness. I lied, it's definitely not a lumbar vertebra. So we're in the lower region of the thoracic vertebra. The reason I can tell that is, well, the reason I should have known that. These are costal facets. So facet is joint. So costal meaning rib. So this is your distal layering. So your ribs come down into T8, T10. So this is the lower part of your thoracic region, because your ribs actually lock into your vertebra through joints, further helping stabilize those. So the trabecula in the arch actually runs continuous to join the vertebral body. So it runs into it and continuous with it, so that strut work is continuous. That strut work is directly connected all the way through. So there we have examples of our different regions. Cervical, size of vertebra smaller is only needs to support head, so we don't have as much cervical body. You need first two vertebrae to function as base of skull and increase mobility. The atlas and the axis are different because they have very unique functions. The thoracic bodies widen to support the trunk, so you've got more weight pushing in, so they've got more base of support. And you also have the costal facets, which is giving us that articulation for the ribs. In some regions, those ribs articulate with the vertebra above and below, which really kind of locks those things in place. We don't have a lot of mobility within the thoracic cavity, and we don't really want it because it's protecting soft, squishy stuff that doesn't want to get moved. Now the lumbar region goes back to where we wouldn't have a lot of mobility. We don't have a lot of ligamentous stability in that area. We have a little bit of locking in place with these facet joints, these articular facets, to help some of that slippage. But that leaves a lot to be held with muscular control. And it's in that we tend to get issues, because people who don't have core activation, they have spines that tend to slip off, which leads to all kinds of issues. So we undermine that stability. So that balance between protection and function that we've talked about throughout the body in other places is very much alive and well here. Ball and socket joints. The glenoid in the shoulder has a high degree of mobility but a low degree of stability. The acetabulum, the hip, is the other way around. So the socket itself grabs onto more of that femoral head, helping stabilize it in place, but that decreases the amount of mobility we can have. So cervical, we have a very high degree of range of motion, but a low degree of protection. Thoracic, we have a high degree of protection with a low degree of range of motion. In lumbar, it's a balance of protection with range of motion to where we need to have a considerable amount of range of motion, but we have a considerable amount of weight, so we have the need to have a stability by muscle. But it frequently takes a little bit of training to help make sure those muscles are firing when and how they should be.
And the coccyx?
So, well, the sacrum is going to be below the lumbar, and because the sacrum and the coccyx are more fused bones, so the sacrum is all one fused set, the coccyx is all one fused set, there isn't a motion that's capable within them. There isn't anything that crosses over the coccyx that would move it independent from the others. We no longer have our tails, sorry, as fun as that could be. So no, they're pretty much ligamentously anchored all over the place and wouldn't dare go anywhere. So sustructural anatomy, things you need to pay attention to. Transverse process, spinous process, facets, the superior and inferior articular facets. Pars interarticularis, and let me tell you where that is real quick, and then the pedicles and the lamina, which we've discussed. So I want that picture. So superior articular facet, inferior articular facet. This space that runs right between them is called the pars interarticularis. So interarticularis means between the articulations. So pars is kind of the bridge between the superior and inferior articular facet. It's a place to recognize because we see injuries with that with certain sports. Gymnastics, cheerleading, where people land and they extend and put a lot of load into these facet joints, tend to get a fracture right in through here, which is spondylolysis. We call it spondy for short. If that progresses and gets worse, then that disc can, that vertebra, the superior proximal, the superior vertebra, can actually dislocate in relation to the one underneath it, which is spondylolisthesis. It's a lot of words, a lot of letters. Once you get to that point, you basically have to go in and wire them back together to help stabilize. Spondylolysis, I can pull you out of practice, let the stress fracture heal, and you can be okay with a bit of core strengthening, core activation. So transverse process is points of attachment for intrinsic muscles. I mean, these projections are there for a reason. Things are anchoring on them. And spinous process, attached for muscles and ligaments all the way up the spine. Angulation relative to vertebra help limit extension. So you'll find that this is C7. That projects directly posteriorly to make it very palpable and pronounced. And as we start getting into lower levels of thoracic vertebra, we end up having increased angulation to help lock those vertebrae in place to where, again, the thoracic cavity is very secure with osteo restrictions. It's not going anywhere, so you can protect the soft squishies on the inside. Keep the form and function for the lungs to work. I think it's trying to put a video. I don't think it can. I don't think that file exists anymore. All right, facet joints. So these are synovial joints. What does that mean? There's a fluid in them, the synovial fluid. It's part of it. There's certain features that synovial joints have.
I think they're freely movable.
They're freely movable joints. They have a synovial joint capsule around them. They have synovial fluid inside of them. So they're meant to move. Medial portion of superior facet articulates with the lateral portion of inferior facet. So the one above it goes with the one below. So it's locking these vertebrae in place so that they can't. They're geared to handle a compressive force predominantly, but since we are so mobile in what we can do, these facet joints stabilize the spine against some of the shear and rotational forces. So it unloads compressive force from vertebral body by 20%. So pedicles, lamina. Connectiform intervertebral foramen, making the archway through which spinal nerves exit the spinal cord. And then there's your pars interarticularis. So this here, that's a superior articular facet connected with the inferior articular facet of the one above. This is the inferior articular facet of the same vertebra. And so this is that pars interarticularis. You'll see it labeled as a Scotty dog fracture for that spondylolysis. So if you look on an x-ray, it looks like a Scotty dog. It's really pretty cool. And then Scotty dog's got a broken neck or he's got a collared neck if he's got a fracture there. And then spondylolisthesis, they call it decapitated Scotty dog, because it looks like his head is separate from his body. Because this would be his head up in here, and then these are his feet, and that's his head falling off. Common site for stress fracture, lumbar spine. So you can see the archways that are made up and through here as these facets kind of create height. And it's through these archways that we end up having root nerves, spinal nerves exiting the spinal cord to then go out and do their thing elsewhere or bring information in. All right, unique locations. Let's go see spine. Atlas, C1. You guys, the Greek mythology, Roman mythology, one of the two. I'm not good with my mythologies. So the guy is standing here holding up the world. That's Atlas, right? So Atlas C1 is appropriate because it holds up the base of the skull. Now it's got this saddle joint, so it's actually kind of got a bilateral saddle joint on either side that helps cradle the skull. It allows for nodding. So just that pivot forward and backwards. Now C1 rests on C2, which is called your axis. Axis being the point of rotation. It has this dens which sticks upwards. So C1 sits down on C2 where the dens protrudes upwards into the ring of C1. And there's something called the alar ligaments, A-L-A-R ligaments, and they project out from the dens into C2 to help stabilize it in that space so it doesn't go anywhere. So we have a long transverse process on C1 with no spinous process. And this is your atlanto-occipital joint, your OA. So C2, dens, sits up onto C1, forms atlantoaxial joint, and this is your point of rotation, hence you having the axis sticking up with the dens that C1 can pivot and turn around C2. And here we have typos. Thoracic spine. Spinous process is angled down to limit extension. They thicken for articulations with the ribs. The ribs articulate with transverse processes T1 and then T10, 11, 12. And then on T2 through 9, there's a superior and an inferior costal facet. So on T2 and through T9, they actually have, like I said earlier, they have this articulation with the vertebra above and below, which helps lock all your Legos together. Sacral spine, which is the anchor of the spine. And I mentioned lumbarization and sacralization, to where you're going into 5, or you're going into 6 or 4. So lumbarization, S1 fails to fuse, acts as an L6. So you've increased the lumbar spine. And then sacralization, L5 fuses with sacrum, so you've increased the size of the sacrum. Now from this image, one thing you'll notice, especially when you get down the lumbar spine, the height of the vertebral body, anterior versus posterior. So they're wedge shaped. They're not uniform all the way across. So the shape of the bone actually helps increase the curvature of the lumbar spine. So you're creating some of that curvature simply by the structure of the bone. Now, if I have this lumbar spine accentuated, somebody who doesn't have a lot of core control, it increases that curvature. You're actually displacing L3, 4, 5 more and more forward of your sacrum. So, if you look at our poor guy over here, the anterior portion of that vertebral body is well in front of your sacrum. So the more this sacrum gets protruded posteriorly, rotated posteriorly, that booty sticking out a little bit, the more that happens, the more that lumbar vertebra is actually directly anterior to the sacrum. So the more you curve, the less you have activation here, the more this curves out, the more that lumbar, L5, L4, L5, shifts anterior in relation to the base of support of the sacrum. That means you're getting away from stacking your bricks on top of each other and more to where this is so positioned posteriorly that the weight of this is just drawing it forward. And you're relying on ligamentous attachments, ligaments that run through the area, to help stabilize. But they're getting stretched over 10, 20, 30, 80, 90 years of life, making this more and more problematic. Or the musculature, which is being failed to be used anyways, or inhibited at that point. So this is why, as we get older, one of the reasons we tend to have more disc pathologies, because we, through bad posture and bad form and bad muscle activation, we weaken the static structures that stabilize that lumbar spine. Cool. So two primary types of articulations of joints. Intervertebral joints, so cartilages between the vertebral bodies. So we have a vertebral body and then a disc, which is a cartilaginous disc, and then another body. So they're kind of stacked alternatingly on top of each other. And then the zygapophyseal joints, which is your facet joints. That's the fancy word, zygapophyseal instead of facet. It works. So, again, synovial, diarthrodial, which all means freely moving. So let's chat discs for a minute. In between these vertebral bodies, we have these cool little discs. They're shock absorbers. Think of them like jelly donuts. They're directly opposite of the vertebral bodies. On the vertebral body, if that was a donut, it has a lot of rigidity. It's more like sandwich bread. It has a lot of rigidity on the outside. Your crust on the outside, so it kind of resists that force. But if you squish it in the middle, it's not quite so built up. There's an internal structure within your sandwich called all the stuff that you stick in your sandwich. It's a very technical term. this being like a jelly donut is a little bit different. The outside is something called the annulus fibrosus. Written at the bottom. Annulus means rings, fibers. So they're fibrous rings that go around it. And those fibers are actually oriented at a 45-degree angle as it goes around. So all of this ring is angled this way. And the next ring out is angled the exact opposite way. And they alternate. So they're geared to handle rotational stress. They're geared to handle shear force and twisting. And that's the outside. And that's comparable to the trabecular, right? So it's the strut work that handles rotation and shear forces. So the trabecular bone is on the inside, but that same resistance to force is on the outside of the disc. So it makes up 20 to 33% of the length of the column. You're taller in the morning than you are at night. Most of that is by the weight and the compression of your body. You squeeze out the water. You go to sleep and you relax and you're laid out and your body rehydrates and it... Does you feel taller in the morning? Obviously. Shock absorbers increase total range of motion for sure. So then we get to the inside of our jelly donut. So the inside of our jelly donut is like a little water balloon. I can squish it and it just goes and it bulges out. But it can handle that compressive force. If I take a water balloon and I twist it, it's going to explode all over me. So the compressive force of the cortical bone, which is on the outsides of the cortical bone, that compressive force, that compressive resistance, is the inside of the disc. You've heard of people having herniated discs? Yeah? So it's a breakdown in the rings of the annulus fibrosus. So you're getting a weakness within the wall, and the jelly donut inside is trying to squish outside. So it's causing a bulge in the rest of the annulus fibrosus because the internal walls are breaking down. So the bulge, the pressure from the loading on it, is pushing that and extending it outward. All the way to the point that you can have it completely extruded to where you've ruptured through the annulus fibrosus and the insides are all over the place outside of your disc. Makes for a bad day. Disc details, there's no disc between skull and C1 or C1, C2, which is atlanto-occipital or atlantoaxial joints. Ratio of disc to height of vertebral body is greatest in the cervical region. And the reason for that is because the cervical bodies of the vertebral bodies in the cervical region are so small. Yes, the discs do get a little bigger, but the vertebral bodies are just so much smaller in the cervical area that because again they don't have to carry so much weight. But it makes that ratio different. Principal concentration of your discs is water, collagen. Collagen is your it's the strut work, the structure of your skin. It gives the elasticity, well, the elastin does. The collagen gives the strength to most fibers. It is what gives the strength to your tendons as you put tensile loads into them. And then the proteoglycans. And the proteoglycans is a mixture of stuff that's pretty much, it is the jelly donut. It's the inside of it that helps give it that squishable nature. But I'm not sure about these collagen types. So annulus fibrosus, collagen arranged in concentric circles. And as we break the system down, the body starts altering the types of collagen it's using to build these rings. So in response to injury, as things break, we tend to put in an altered ratio which weakens the system in general. So this is actually a cool image because you can see the direction of the fibers crisscrossing as they're oriented at opposing angles as you go through them, which I thought was cool. The nucleus pulposus is semi-gelatinous, so it's like putting jello inside. 60 to 70% water, deformable but not compressible. So it is the resistance to those compressive forces. There you go. Okay, last pieces. Motions. 3 degrees of freedom, flexion, extension, rotation, and then tilting, lateral bending. 3 translatory motions, forward glide, lateral glide, compression, and distraction. So we got a lot of movement we can have with this. When we hit muscles, we will definitely get into the flexion extension. We will get into the rotation. Lateral tilt, the tilting and lateral bending is going to come from these same muscles up in here, but they're firing on one side versus bilaterally, which is going to cause that tilt or that rotation. Nope. Still trying to make that one thing work. Quit it. All right, so imaging. So you go into extension, you lean back, and those discs, it puts increased pressure on the back, bulges them forward just a little bit. Likewise, left bend, puts my transverse processes closer together, the edges of those vertebral bodies closer together, and the disc just kind of deforms and squishes inside, helping stabilize and hold it in place. Forward flexion, and it pushes it backwards. Now recognize that if we have any kind of significant disc protrusion, then what's running in through these gaps, again, is nerve roots. So if you have a herniation, a disc, some of that nucleus pulposus pushing through at any of this, then it's compressing on a nerve, which is going to cause you issues somewhere down the line. That being said, we can take an MRI, and most people, especially when they hit middle age and above, have some level of disc herniation. There's evidence that there is a bulge within the disc somewhere. But most aren't symptomatic. So just to have an image that shows that there's an increased bulge in a region is, even if you have sciatic or sciatic nerve root irritation, even if you have symptoms that can be tied to that nerve being impinged, just seeing a bulge doesn't inherently mean that's the location that's creating your problem, because it could have been there already without any symptoms whatsoever. It makes dealing with back pain and radiculopathy, that radiating nerve pain, all that much more difficult to deal with. Because yes, I see this and it's bulging, and that may not have anything to do with it whatsoever. So it makes it troublesome. All right, so if you go back into there, where we have translatory motions of forward glide, lateral glide, compression, distraction with rotation, tilting and lateral bending, we create motion in the spine by coupling these kinds of motions together. Very rarely do we have unidirectional motion at any given time. So consistent association of one motion about an axis with another motion around a different axis. So we don't have much for uniplanar motions. And the way it functions is different from one region to the next. So examples. Lateral flexion, left lateral flexion, the mid-cervical, lower cervical, and upper thoracic rotation to the left, and forward flexion. So for me to move this way, my upper spine is actually pivoting as well as flexing. So there's rotation with flexion going on. So rarely do we ever have it to where it's a single region doing one motion. Mid-thoracic and lower thoracic, rotation to the right or left and forward flexion, and then upper lumbar, lower lumbar, lumbosacral. Again, looking at that left lateral flexion idea is rotation to the right or left and forward flexion as well. So we're combining motions, combining movements to get the components that we have. So what are the determinants? The spinal posture and the curves. How much curve you have is going to change the angles that your transverse and spinous process and the articular facet joints are all kind of aligned. Orientation of the articular facets. The fluidity, elasticity, and thickness of the discs. If you have rigid discs that aren't going to move much, it's going to limit some of that, which means you might have to have a compensatory motion at a different articulation site. If the discs aren't giving enough, then we have to create that motion secondarily. Extensibility of muscles, ligaments, and joint capsules. If things are overly lax or overly tight, then it's going to change how those dynamics work. So it isn't one thing that you memorize saying, left motion is rotation and flexion. It is for everybody. It's more of those as a pairing, but the degree to which you have each of those is unique to the person based upon the range of motion they have. They have a whole field of this called chiropractics, for the most part. I mean, they're looking at this spinal alignment to make sure that it's optimally decompressing the nerves as they leave the spine, with the intent of optimizing that nerve function, which optimizes organ function. Your stomach might get upset because the way those nerves that innervate the stomach leave the spine are getting impinged from you having a restriction at this location. So fix that, correct that rib, it unloads the joint, the vertebral bodies and the facet joints working together, which unloads the nerve, which makes your stomach feel better. That's a bit of their theories. And we are definitely not. Definitely not. That was